In 2007, under-engineering, lax regulation, ever-increasing static load, combined with ongoing inadequate inspections, led to the deadliest structural collapse in Minnesota's history. When we head out on the road, whether it be our daily commute, a trip to the store, or simply for fun, we are, by default, putting ourselves at much greater risk due to the inherently dangerous nature of driving on its own. The risks of driving are due to many factors, most of which, though, drivers are expected to remain keenly aware of when sharing the road, stopping at red lights, yielding to traffic, observing speed limits. A number of factors we're expected to keep an eye out for at all times. However, the integrity of structures used for carrying this traffic is, quite reasonably, not something we're ever expecting to crumble out from under us. On Wednesday, August 1st, 2007 though, at roughly 6 p.m., a busy time for evening commuters, the main deck portion of the I-35W bridge in Minneapolis, with more than 100 occupied vehicles and 17 construction workers aboard its deck at the time, collapsed suddenly into the Mississippi River below. This catastrophe claimed the lives of 13 people, and 145 more would be injured. 1,000 feet of the nearly 2,000-foot-long, 8-lane bridge had fallen away, roughly 450 feet of which falling into the 15-feet-deep waterway below. The initial scene was overwhelming, and many were understandably panicked. Motorists nearing the span that had just collapsed began turning around and driving away frantically. Those on board the bridge's now precarious approach spans that were left still standing began fleeing their vehicles as virtually everything in their field of vision had just dropped away instantly as they were commuting, and into a cloud of dust, chaos, and confusion below.
Folks, we're looking at a surreal scene right now. Just to bring you up to date, this is the 35W bridge over the Mississippi River. It has collapsed. By our crew's estimates,
Citizen first responders on the scene numbered over 100 plus. Construction workers just then leaving and arriving for their shift, students and staff from the nearby University of Minnesota campus, medical personnel from the nearby Red Cross building, in addition to many brave passers-by, many of which entering the river, pulling construction workers and motorists they could reach to safety. The collapse took place at roughly 6 p.m., and by 6:10 as the first Minneapolis police and fire units began to arrive, eventually totaling 19 fire engines, a command post was quickly established by authorities in the Red Cross building's parking lot nearby. By 6:14 p.m., the Hennepin County Sheriff would be the first to arrive on the water and begin conducting rescue operations in those areas where stricken vehicles had been trapped in the river. Hennepin County Medical Center initiated its disaster plan, calling in more medical personnel, readying local hospitals, and dispatching all ambulances available to the rescue site. The Sheriff's Office would establish their River Incident Command Center by 6:25 p.m. on the north bank of the river near the University of Minnesota's River Flats. This was the closest point on the riverbank with enough boat ramps for such a rescue effort. Before the first hour would be over, 12 public safety agencies had arrived, bringing a total of 28 watercraft to assist with the precarious river rescue. By 7:27 p.m., command of both operations declared all water teams would go from rescue to recovery. On August 2nd, the following day, the U.S. Coast Guard arrived on scene to form a temporary security zone from the upper St. Anthony Falls to the lower portion. And at 7 p.m. that same day, command of the scene was transferred from the Minneapolis Fire Department to the Police Department, as it would then be declared a crime scene due to the possibility of an extremist attack being the cause. By August 4th, the Hennepin County Sheriff's Office requested further aid in underwater search and investigation. The FBI's USERT, or Underwater Search and Evidence Response Team, and U.S. Naval Sea Systems Command diving and salvage teams arrived on the 5th and 6th, respectively. By the time this monumental rescue and initial investigation had been completed, a total of 190 people were confirmed to have been on the deck or near the bridge at the time of the collapse. Of the 190, 13 were fatalities, 34 received serious injuries, 111 received minor injuries, and 32 were either uninjured or unknown. The matter of bridges and their construction in the United States is complicated, much like the country's infrastructure issues in general. While regulation, budget, and maintenance standards can vary greatly from state to state, so too can overall climate and topography, as the nation runs the gamut from coastal marine environments, dry southern deserts, to harsh long winter climes, where road surfaces have been heavily salted for decades. Designated Bridge number 9340, commissioned by the state of Minnesota's Department of Highways between 1964 and 65, Bridge 9340 would be designed by Sverdrup and Parcel and Associates, with these designs ultimately signed off on and approved by then named the Minnesota Department of Transportation. Its deck approximately 115 feet above the lower end of St. Anthony Falls, the bridge would ease traffic congestion crossing the Mississippi into and out of this bustling portion of Minneapolis, by allowing vehicles to cross at highway speeds, at the time 50+ miles per hour. The bridge was built by Hercon Incorporated, with steelwork of the structure engineered and staged by the Allied Structural Steel Company, which was also the steel fabricator for the project. The I-35W bridge would be an 8-lane, arched, Warren-type truss deck design, with the main deck being supported by 4 main piers. This allowed for a relatively high clearance to the river below and an unobstructed, Spartan, minimalist upper deck. Completed in 1967, it opened in November to traffic being diverted from another bridge in the area undergoing renovations, and would take on the I-35W highway traffic starting in 1971. Once rescue and recovery operations had been completed, the final victims' remains were pulled from the wreckage reportedly on August 21. It's easy to say hindsight is 20/20 due to the plethora of factual information we now have regarding this tragedy. However, at the time, it cannot be overstated just how much of a mystery this collapse was for investigators initially. Much like the NTSB would piece together a stricken aircraft when investigating an aviation accident, many somewhat similar methods would be required here. Important to note, though, is that during rescue and recovery operations, even salvage operations intended directly for investigative purposes, it's difficult, and in many instances impossible, to recover such massive objects like stringers from the deck, main truss members, and other similar connected structures without torch cutting, shearing, twisting, and causing further deformation in simply attempting to relocate them. Investigating and piecing this puzzle together, much of which taking place at the Bohemian Flats Park nearby, where salvaged members were reconstructed and examined, would be a lengthy and laborious process, all while trying to make heads or tails of what was evidence from cause versus deformation from rescue and recovery. However, as if to foreshadow future findings, and in addition to authorities being well aware there was much construction load that day parked on the main deck, on August 8, 2007, only 7 days after the collapse and well before any conclusions had been reached, the Federal Highway Administration issued Nationwide Technical Advisory 5140.28 regarding construction loads on bridges. While no conclusions have been reached, in an abundance of caution, we strongly advise the state transportation agencies and other bridge owners who are engaged in or contemplating any construction operation on their bridges to ensure that any construction loading and stockpiled raw materials placed on a structure do not overload its members. Participating in the investigation alongside the NTSB were reps from the Federal Highway Administration, Minneapolis Department of Transportation or MnDOT, Hennepin County Sheriff's Office, and a contractor from the company that had been performing work on the bridge the day of the collapse, Progressive Contractors Incorporated. The on-site investigation and analysis required many investigators remain present all the way through November of 2007. Beyond this, though, lab analysis and further investigation by the NTSB would continue well into 2008, with their final report being released on November 14th of that year. It simply can't be overstated the amount of effort and dedication it took from authorities to piece this puzzle together. After pouring through reams of PDF after PDF myself from both .edu papers and the NTSB's 178-page report, my typical routine for these videos, this time it's a bit different. Covering the sheer volume of factors they had to unearth that could have led to this failure, buried in documents, designs, and inspection history over a period of 40+ years, would make this video far too long. And, as is typical with disasters of this nature, it's almost always down to a lengthy chain of failures and mishandlings. Rarely is there a single party or cause to blame. This one just happened to undergo these changes so slowly and hidden behind such a deeply entrenched lack of awareness, even by experts regarding key areas where the bridge failed, even would-be warning signs would go undocumented when photographed or completely overlooked during inspections, as a crucial load-bearing portion of this steel deck truss design was not well understood industry-wide until this collapse took place. But I will attempt as thorough a summary as I can. The I-35W bridge had been designed and built prior to metal fatigue cracking being well understood. In the late 1970s, when a better understanding of metal fatigue cracking was established within the industry, deck truss bridges such as the I-35W bridge were recognized as being non-load path redundant, or fracture critical. That is, if certain main truss members failed, the bridge would collapse. It was well known that the I-35W bridge was non-load path redundant. It's also well known as of 2007, 19,273 U.S. bridges are non-load path redundant, or fracture critical. While fracture critical bridges are of outdated design, this term basically means they're more susceptible to major partial or total collapse if even just a single load-bearing element fractures. It's not inherently unsafe according to officials, but I'm going to go out on a limb and say that a bridge that is left standing after single or multiple structural failures is safer than one that doesn't. When analyses of main trusses in tension and compression, amongst other load-bearing members like lower chords and floor trusses, revealed no major failures, the attention was turned to what's referred to as nodes, a connecting point, or to oversimplify, the joint where upper and lower chords join to meet vertical and diagonal members in tension and compression. Some of the major findings ruled out as caused by this point were the fracture of a floor truss, pre-existing cracking in the bridge deck truss or approach spans, temperature effects, and shifting of the piers. Narrowed down to the nodes now, a crucial part of these joints, the gusset plates, which unite these diagonals, verticals, and chords on either side of each joint, would essentially be put under the microscope.
Our working theory and our knowledge that tells us that it is the gusset plates, beginning with the U10, that the failure was created.
The gusset plates had basically separated, torn apart as if these joints had been burst through in a lateral motion. The I-35W bridge did have expansion joints, rocker bearings, and roller bearings to allow for longitudinal movement due to thermal expansion and contraction, along with sway braces and lateral braces to ensure rigidity in lateral movement. When closely examining the gusset plates, there was corrosion damage, but testing bore out that it was within acceptable limits. Upon comparing them against the original designs for the bridge, this too was found to not be the culprit, as the gussets examined matched the original designs and prints for the structure. They were neither fabricated nor implemented outside of those design tolerances. However, after much testing of thickness, material type, and other analyses, these gusset plates were found to have been physically inadequate for their intended loads. This could only stem from one factor now. The original designs, for whatever reason, did not call for these gussets to have adequate capacity to begin with, not even for the original designs of the bridge, let alone the dead load and live load that would be added as time went on. In 1977, a renovation to increase deck thickness, ironically, a solution by MnDOT to battle ongoing effects of road chemicals that had been corroding rebar on the top deck of bridges in similar climates. This would be 2 inches of low slump concrete across the entire deck, bringing the deck thickness to over 8 inches and adding more than 3 million pounds of static or dead load. In 1998, work began to replace median barriers, upgrade concrete traffic railings, improve drainage, repair slabs, retrofit cross girders, and due to the high volume of ice-related accidents during winter months, install an automatic anti-icing system that employed the use of sensors, 38 valve units, and 76 spray nozzles to apply potassium acetate onto the road surface when necessary, a significantly less corrosive alternative to salt brine. In all, the 1998 upgrades and repairs added another 1 million plus pounds of dead load. Also important to note here is that during these renovations, live load factors of the construction vehicles, the staging of materials like temporary piles of aggregate, and other similarly heavy equipment and supplies, has the potential to increase load factors on the bridge while present by hundreds of thousands, even millions of pounds. And it's not always the case. These loads can be evenly distributed. Many times they're localized or even heavily congregated around individual locations. Which leads us to the renovation project that began in June of 2007, just 2 months prior to the collapse. Progressive Contractors, the construction company performing this maintenance, was carrying out the seemingly routine tasks of removing 2 inches of top deck concrete or milling to be replaced with a fresh 2-inch layer, replacing and patching weathered and worn curbs, reconstructing expansion joints, and replacing aging spray discs and sensors of the anti-icing system. This work had a final completion date planned for October 26 of that same year. As we all know, it was not to be. Jacobs Engineering, the company who acquired original designers Sverdrup and Parcel, was cooperating and assisting in the investigation. However, amongst all the original prints and plans they had on record, they were not able to produce records that showed calculations for nodes on the main trusses. In sort of an ironic twist, a former unnamed Sverdrup and Parcel employee had, for whatever reason, personally retained some of the much-needed records of these node and gusset plate calculations. These records showed the breakthrough investigators were looking for. Sverdrup and Parcel had done their homework, and for the I-35W bridge, virtually all of their calculations and designs for dead load, live load, thermal expansion, main truss loading, cross members, and the like were found to be valid. The NTSB even determined they had known full well how to design nodes and gusset plates, and even properly calculate their tolerance to stress effects. But for Bridge 9340, the effects of chord carry-through forces were all that was found to be factored into the size, number of rivets, and rivet patterns for the gusset plates. The diagonal members and capacity needed to bear their lateral load was completely omitted from all calculations and designs signed off on by the then-named State of Minnesota Department of Highways. Longitudinal movement is typically much greater than lateral movement in bridges like these, thus the need for expansion joints and roller bearings. But despite lateral or sideways movements seeming minimal comparatively, they still exert a massive amount of force on all supporting members. Over time, lateral motion where the tops of diagonals met all 4 U10 joints would deform these under-engineered gusset plates back and forth over the previous 4 decades to the point where total fracture was imminent. Ironically, these photos you're seeing here of the bowed gusset plates on all 4 U10 location nodes were taken during inspections, specifically inspections as recent as 2003. And if you're like me, you might be asking yourself, how would trained inspectors not notice these deformations? I mean, they may appear minimal to our untrained eyes, but this is what these people are trained for, isn't it? Well, unfortunately, no, quite the opposite. See, even up to, well, not all that long ago, gusset plates and their nodes have been, to oversimplify, little more than an afterthought for all bodies regulating this stuff in the U.S. According to the NTSB, neither federal nor state authorities evaluated the design of the gusset plates for the I-35W bridge in sufficient detail during the design and acceptance process to detect the design errors in the plates, nor was it standard practice for them to do so. And as of the report for this collapse even, the NTSB also concluded current federal and state design review procedures are inadequate to detect design errors in bridges. So, yeah, we'll come back around to this bigger picture issue here shortly. But the overarching theme here regarding the inspections can be summed up in the attitude of a professional safety engineer, one who specialized in fracture-critical bridge inspections, who observed the deformation of these gussets in 1997, and when interviewed stated, "That's construction. That's original construction," as if to dismiss the bowing of gusset plates as some sort of original construction issue and not cause to have been concerned. He'd go on to say, "Gusset plates are over-designed. The safety factors within those gusset plates are 2 to 3. Again, some sort of dismissive assumption meaning all gusset plates are engineered to be 2 to 3 times more robust than required, a conclusion he claimed was reached because that's the way they taught it at his undergraduate school. He would also state, "Our inspections are to find deterioration or findings of deterioration on maintenance. We do not note or describe construction or design problems." So by the day of collapse, that renovation project had been underway for approximately 2 months. Construction materials, equipment, and vehicles had been parked directly above Node U10 West, with the heaviest portion, piles of aggregate weighing in at nearly 400,000 pounds, being within closest proximity to the soon-to-be failure point. Traffic was also reportedly bumper to bumper, as it was both near rush hour and, due to construction, the road work made the bridge somewhat of a bottleneck. Once this node gave way, since this was a fracture-critical or non-load path redundant bridge, total collapse of the main deck was inevitable. With fractures of the other weakest points, the other U10 nodes following shortly thereafter as the main deck gave way. According to the Federal Highway Administration, of those 19,273 bridges in the U.S. that are considered non-load path redundant, about 465 of them have a main span that is a steel deck truss. And as of the NTSB's report in 2008, because current American Association of State and Highway Transportation Officials guidance directs bridge owners to rate their bridges when significant changes occur, but not before they place new bridges in service, the load carrying capacity of new bridges may not be verified before they are open to traffic. Had American Association of State Highway and Transportation Officials guidance included gusset plates in load ratings, there would have been multiple opportunities to detect the inadequate capacity of the U10 gusset plates of the I-35W bridge deck truss. And also something I find a bit unsettling. Although the I-35W bridge had been rated under the National Bridge Inspection Standards as structurally deficient for 16 years before the accident, the conditions responsible for that rating did not cause or contribute to the collapse of the bridge. I'm reading this as the failure to understand nodes and their gusset plates by the industry meant inspections that already found several deficiencies were still overlooking many even more critical deficiencies. Many recommendations were made by the NTSB following this incident, obviously, but in America's political climate it begs the question, what progress has actually been made? Well, it's not all doom and gloom, as many states had already begun to step up even prior to this incident. The industry just needed a push in the right direction as to what they should be actually looking for, instead of looking for excuses. As a former safety guy for OSHA, I can honestly say, regardless of political outcomes from these incidents, and whether or not budget allows it, the hard lessons learned, like inspecting and testing gusset plates properly, the people who care about this stuff, as few as they may be, will push for standards to be changed, awareness to be raised. For instance, the Federal Highway Administration immediately began pushing out their technical advisories, even before the NTSB's report was finalized. Much of this stuff takes zero budget and no politics, just people who care enough to push for it. America's approach to infrastructure still leaves much to be desired, of course, but apathy or lack of awareness is pervasive. No amount of policy changes and political grandstanding will change human nature. But raising awareness, word of mouth at the day-to-day 9-to-5 level, that's invaluable. And industry-wide in the U.S., this incident, for many hidden engineering and technical issues, was a wake-up call regardless. The I-35W St. Anthony Falls Bridge, a sturdy concrete box girder design, would be constructed in its place quite rapidly, but of course under heavy scrutiny. The Minnesota Department of Transportation even kept a web page updated with weekly updates and other interesting facts about the new bridge. It would open just 13 months after the collapse in September of 2008. A memorial garden can be found directly to the west on the south bank of the Mississippi between the upper and lower falls, just 1,700 feet away.